All right, good morning and thank you all for joining us. It's our pleasure to welcome all of you to the final session of the four-part symposium, Technological Revolutions in Art History, co-organized by the Frick's Digital Art History Lab and the Museum of Modern Art. I'm Robert Kassler, Director of Imaging and Visual Resources at MoMA. The goal of the symposium is to encourage the connection of the computer sciences with the field of art history. The first three sessions of the symposium have explored the historical links between art history and science and technology, how the invention of photography impacted the study of art, and how other current technological breakthroughs have the potential to promote new developments in the field of art history. And most recently, our presentations explored the ethics of digitization and how issues regarding access and discoverability impact research in art history. Presentations in part 4 of the symposium will take the format of lightning rounds, most 7 to 8 minutes, and highlight recent computational art history projects and other initiatives that expand the access and discoverability of the digitized collections from a variety of cultural heritage sites and institutions. The theme for the first half of the lightning rounds is artificial intelligence and cultural heritage collections. The talks will encompass the use and understanding of technologies that allow us to place digital representations of objects, artifacts, and locations into machines that can mimic the cognitive functions of the human brain, including reasoning, learning, language processing, and visual perception. Current capabilities in AI can compile this information and provide new insights, new stories, new relationships, and understandings that were not previously available or accessible. In order to understand the great evolving capabilities and time-saving efficiencies AI affords, we must also strive to be aware of their limitations and biases. In the second hour of today's presentations, entitled Visualizing and Preserving Art Historical Narratives, we will explore blockchain and neural networks in relation to their recent applications within the cultural heritage field, and witness an artist's analog project transformed and expanded by powerful new digital initiatives. In the interest of time, we will not be giving formal introductions for each speaker, but you can find links to the speakers' full bios in the chat box. We will divide the session into two one-hour parts and hold a question and answer period at the end of each. So as questions arise, feel free to type them into the Q&A box. The Q&A will be run today by Samantha Deutsch of the Frick, and Samantha, I'll be helping you out with that. So to get us started, we have Leonardo Impet, Assistant Professor of Computer Science at Durham University, with a presentation, Convolutions as Symbolic Form, Bias in AI, and How Art History Can Help. So Leo, I'm going to turn it over to you now.
Great, thanks so much. So thanks for that wonderful introduction, and thanks also to the organizers for what looks like a great event and what has been a great series of events so far. So I'm Leo Impet from Durham. I'm at the AI and Human Systems group. We don't have a great deal of time, so I'm going to get straight in and give you the overview of my argument. Now, we won't have time to go into all of the subtleties, but this is the argument. Computer vision systems are a set of hypotheses about how images work. They don't assume a set of hypotheses, that's what they are. Not all of these hypotheses, but many of them are historically dependent. Even the ones that seem to relate solely to human psychology, like color perception, end up being wildly culturally and historically dependent when you look at them. And lastly, sorry, it's scattering away. Lastly, art historians have been studying historically dependent vision for as long as art history has existed. I borrowed the title of this talk, of course, from Panofsky, but of course we have it in Wulfflin, Augengeschichte, in Baxendale's Period Eye, and more recently in Tobias Teutenberg's Historical Perceptology. I also want to make it clear that I'm not a skeptic about computer vision in art, and I think a great many discussions of bias in AI have been a little bit sort of politically and technically naive. So most of my work for the past 5 years has been on computer vision for the distant reading of visual art, first on gesture, on Arby Warburg and gestural iconography, then on luministic effects, especially what I call counterfactual optics, so sort of situations which couldn't physically exist, such as divine light. Then on pixel-wise segmentation for a kind of iconoclasm where you can get rid of most of the image and concentrate on what's left. So looking only at the backgrounds of portraits or looking only at the draperies of paintings in this case. And finally, in trying to sort of democratize computer vision through a visual programming language called ImageGraph, which you can find on the link there, imagegraph.cc, which is basically a sort of open source web app where you can drag and drop and build your own computer vision system and run it without needing to code in Python. All right, so without sort of trying to sound like I'm an incorrigible naysayer about computer vision in art history, I do, however, want to highlight the other side of this equation, which is that I've always had another foot in another field, which is that of critical computer vision. So this is an interactive artwork that you might have seen when it was live in 2019 by Trevor Paglin and Kate Crawford called ImageNet Roulette. And it uses a provocative machine vision system to expose many of the problematic categories that were included in the original ImageNet database for visual classification, which is one of the databases that most standard neural networks have been pre-trained on. And another little plug here, Paglin and Crawford's article is one of a number of exciting contributions from Nick Mertzhoff, Lev Manovich, Luciano Parisi, Matteo Pasquinelli, Benjamin Bratton, and many more that are appearing in a new issue that's just come out that I've co-edited called Ways of Machine Seeing. All right, anyway, so Paglin and Crawford's piece is really about database bias, which is by now a fairly well-studied element of computer vision. And the kind of bias I'm talking about is instead what we call model bias, so in the algorithms themselves. Okay, so how do these two worlds, sort of applied computer vision for art history and critical computer vision, meet? I think the answer is in a rarely cited book from Baxendale, which only has 3.5 stars on Amazon, called Shadows and Enlightenment from the early 90s. And he tells the story of Enlightenment drawing alongside Enlightenment philosophies of vision, which are explored in turn through answers to a simple thought experiment called the Molyneux problem, which basically says, imagine you're blind from birth and you're taught to distinguish between a sphere and a cube just by holding them. Well, one day you can see again. Can you tell which one is the sphere and which is the cube from the other side of the room, but just by seeing them? So the problem isn't just to do with touching and vision, but between seeing and knowing and the role of knowing in seeing. And we get answers from Locke, Condillac, Berkeley, Leibniz, Voltaire, Diderot, Helmholtz. So you're able to chart the whole Enlightenment sort of way of seeing as answers to Molyneux. But this is where Baxendale's radical statement, and I think most interesting point, comes in. He says, if we're going to think about modern thinking about vision, if we're thinking about new thought experiments, we have to replace Molyneux with computer vision, essentially, with a confirmation of circuitry controlled by such and such a program, as he puts it. In other words, computer vision is not just a tool, but I quote here again, a medium in which perceptual processes can be modeled for study, end quote. All right, so Baxendale spends pretty much half the book discussing different computer vision algorithms, but he doesn't use any of them. He's not interested in object detection or visual search on a big database of paintings. Not that those aren't good things to do, but that's not what he's interested in. So instead, each algorithm is a kind of thought experiment which embodies a certain understanding of how images lead to information. So again, the relationship between seeing and knowing. And the period in which he was writing, the early 90s, coincided with a particularly interesting crisis in AI, sort of between neural networks and GOFI, rules-based approaches, expert systems. And he was acutely aware of these two competing paradigms, and he saw them as embodying historical debates about vision. And he went so far as to suggest that, I quote here, neural networks would have pleased Condillac more than Locke, end quote. All right, so in some ways, that debate, or versions of it, sort of between top-down and bottom-up vision, is still alive today. We don't have time to go into all of this, but it's especially a debate about the theory of vision that computer vision systems are built on. In other words, how do you explain the role and the processes of human vision in the first place? And the two main contenders for that historically have been David Marr and James Gibson. And in brief, Marr sees the purpose of visual perception as the inverse of computer graphics. So the role of vision is to reconstruct a precise 3D model from a still 2D image. It's a sort of window metaphor. Whereas Gibson has a much more dynamic view. He sees the purpose of visual perception as sort of evolutionary. You have eyes moving across the page, you have spatial awareness. So spatial awareness in an image is linked to finding escape routes out of a certain situation and things like that. And this debate is especially important in how we treat man-made images, right? Do we treat them as windows onto a consistent 3D world, as you can probably get away with for some early modern European visual art? Or do we treat them as traces of dynamic events, as a series of brushstrokes that happened in a particular order, that have a particular direction, a particular relationship, hierarchical or logical or aesthetic between them? Now, you won't find Marr cited that often in computer vision anymore, but he is absolutely there. So anytime you do depth reconstruction, 3D object detection, neural rendering, a lot of the things that we do and we teach in computer vision, that's all based on Marr's idea of how vision works as inverse graphics. And the recent surge in funding for self-driving car research, where it's really important, obviously, to know where things are around you in 3D, has really pushed this direction a lot. Other innovations, other technical innovations, even recently, like attention networks, which simulate the physical movement of the eye across the page, have moved in the other direction, the Gibson direction. I don't want to advocate here, by the way, that Gibson is better than Marr. I think he's maybe more appropriate for looking at man-made images, but the point is they're two historical theories of how vision works. Neither of them is the most up-to-date sort of cognitive neuroscience theory or anything like that. These are two sort of computationally translatable paradigms for the role and the mechanism of vision. And they come out of their particular historic conditions. So the particular disadvantage that Marr poses for looking especially at man-made images has also been debated in the technical community, just in the case of regular computer vision, let's say. And that disadvantage is that it doesn't let you model situations with inconsistent stimuli. So situations where you have different bits of the image that are contradicting each other, that don't form a totally consistent 3D world. All right, I've finished my time already, so to conclude, here's the argument again. Computer vision systems are a set of hypotheses about images work. Many of these hypotheses are historically dependent, and art historians, I think, have a lot to say about historically and socially dependent visual perception. I've included just a brief list here of sort of specific technical things that make specific assumptions about how those images work. That's it. Thanks so much. I look forward to the questions, which I think are at the end of the session, and to the next speakers.
Hello, I am Damon Crockett. I'm the principal data scientist at the Institute for the Preservation of Cultural Heritage at Yale University. And I'm going to discuss today a method for measuring the condition of photographic collections using computer vision. And I'm going to make, very briefly, a more general argument that condition surveys can and should be automated. So this is a carte de visite. Or visit card. It's a small, in this case, albumin photograph mounted to a card. And the Yale Center for British Art has a large collection of these, about 1,000. Here's the entire collection. And so we can ask the question, well, let's say we want to assess the condition of this collection. How would we do it? Well, traditionally, we would take a sample. And here's the sample, and we would sort of look very closely. We would have a human expert sort of zoom all the way in and look closely at all of these individuals in the sample. And then make some determination about the condition of this item and all the other ones in the sample. And then there'd be some kind of extrapolation to the collection as a whole. So this approach is pretty time consuming, at least relative to what I'm going to talk about. And though it is deep, sort of the human expert, digging deep into, for example, this item here, could yield something very thorough, something very deep, but you get sampling error unless you, do this with the entire collection. You're taking a sample. So you're going to be missing some items completely. And if you do measure the entire collection, it's going to take forever and be really costly. Moreover, this is pretty coarse grained. It would have to be if it's just using human perception at one point in time, right? And so it'd be very difficult to detect very small changes over time. But I think the worst of all is that this method is not exactly repeatable, and it can't be audited. We don't know exactly how it's done. I mean, even the person doing it probably doesn't know exactly how they're doing it. They can't audit all of the internal processes going on. And so we can't make the exact same assessment at two different institutions using different experts, or even the same expert at two different times. Human perception is very context dependent, and it's not designed for something like this, for a task like this, which requires extreme context independence. Now, of course, there are ways to make the human judgments less context dependent by using certain fixed reference points, like here a color target. But if in the end, we're simply having the human make a set of purely objective judgments against fixed reference points, then we might as well automate the process, since this is exactly what computers are great at. So our method is to use the machine to sort these items by condition. And it's a little easier to see if you crop the mats out. And in fact, here now we can zoom out to the entire collection, because it's just as easy to run this on 1,000 as it is to run it on 300 or something. So how do we do this? Well, first is that we have to, if we're relying very precisely on the colors of these things, we have to do color correction. So we include a color target and we perform this color correction. Here, this was done in Photoshop, but it can be done a lot of different ways. So here we've removed this like red tint. And then once we've done that, then we sort of, crop out the area we want to look at, and we run a computer vision algorithm on it. But we're not going to use the sort of modern computer vision algorithms are criticized as being relatively opaque. And I agree. They're usually trained on massive data sets that we are not able to explore and understand. And then sort of the reasons for their making the judgments that they make is not always clear. There are some ways of elucidating that, but in any case, it's usually fairly opaque. And our algorithm is not like that. Ours is very simple, transparent, and it can be decomposed into elements that any conservator would understand. It also doesn't need any training data. So all we're going to do here for albumin photographs is look at yellowing. So on the left, we have a very yellowed image, and on the right, one that hasn't yellowed. And we're going to look at fading. So on the left, a very faded image, and on the right, a very sharp image, even though they're roughly the same age. So we start with a photograph, and this is not in the collection. This is Peter Lorre, but it's just a good photograph to use as an example here. Okay, we find the area of minimum silver density, the brightest area, and we measure color saturation there. So the difference between these two things. And then we find the maximum darkness, and we see how close to pure black it is. And then we combine those two measurements into a general measure of condition. So here are some of the results. These are some of the very bad ones that the computer identified. These are some middling ones, and these are some really good ones. So now you might ask, okay, well, maybe this works for yellowing and fading, but what about other kinds of damage, other kinds of aging? So let's look more closely at this one. So this one was deemed by the machine to be in very good condition, but we notice there's some spotting here. And in fact, there is yellowing in some places. So our method of just sort of identifying D-min and then checking for yellowing there didn't work. But I picked this out as an example because it should be pointed out that, you know, the algorithm we're using in a sense is kind of arbitrary, right? What I'm arguing for here is the system itself, and the algorithms we're using can be swapped in and out. So if we think, for example, that it'd be better to look for yellowing anywhere in the image and not just in that one place, then we would have caught that. Also, other kinds of damage like this spotting can be modeled as textures and can be easily detected by computer vision. So the idea here is we don't even need a single method. Any method can be, you know, plugged into the system and run and rerun, and this can be done ad infinitum. Also, this is actually really important. If you redigitize your collection, for example, 10 years later, now you don't even really need to look for these things analytically. You can just, you know, use a simple measure of change from point 1 to point 2. And then that can be, you know, and so items that have changed a lot, then you can focus on, right? So once you've digitized more than once, you now have this much easier way of detecting change over time. So, okay, so this approach has a number of advantages relative to the traditional method. It's much faster. These 1,000 images took about a minute. It's highly modifiable, as we said. The various models of condition can be swapped in and out. It's also very easy to audit and check. So here we could say, oh, well, this is where we took the measurements, and we know exactly where they were taken, for example. We know the exact measurement process. It's also very precise and can detect very small changes over time. It measures all individuals in the data set. So here we have every individual has a measurement. But most importantly, it's repeatable. And this makes collections comparable across time and space. And it allows you to ask interesting questions like, for example, these are images taken from Henry Fox Talbot's collection. Some of them are bound into copies of his Pencil of Nature, this sort of photo book, the first photo book. And some are not, were never bound, but they're from the same negatives. The ones that were bound, we found faded much worse. Right. And now we have this interesting scientific question that we can explore further. We wouldn't have even been able to ask this question without this precise kind of highly repeatable standard for measuring these things. And so because of all these advantages, we're recommending that this be the way that condition surveys are done. Obviously, there's a lot of details, you know, that would be worked out if you were implementing something like this, but this is sort of a step in that direction. So, thank you.
Slide appearing. My name is Paul Messier. I'm the chair of the Yale Institute for the Preservation of Cultural Heritage, and I'm also the director of the IPCH's Lens Media Lab, which is the same place where Damon works. So, Whimsy. Toward an AI machine vision approach to watermark analysis. What is Whimsy? One of the things I learned from Rick Johnson is it's not an official project unless it has an acronym. Whimsy stands for Watermark Imaging System, which is something I've been working on for maybe 2 years now. Watermarks in paper, well, especially Western paper. This is a piece of handmade paper, laid paper, so-called laid paper was the paper that was introduced. It was the paper making technique that was developed in the 12th century in Europe and really dominated until the middle of the 18th century. When another type of paper was introduced. And if you look at a sheet of laid paper and transmitted light, the light coming through the sheet, you see some very distinct characteristic patterns. Just draw your attention to these vertical so-called chain lines, these horizontal, more finely spaced laid lines. And then there's a design here, which is actually a piece of wire woven into this mesh. What we're looking at actually is a density map of where the pulp settled in during paper making around this wire screen. So we're looking at really it's an image of the mold, the paper making mold. And just looking at a little more detail here, I mentioned these are the chain lines. These are the more widely spaced lines that were running vertically in the previous image. Laid lines running horizontally, more finely spaced. And then there's that watermark, which is this design, which is woven into this mesh effectively with a piece of wire. Again, visible in transmitted light. Recent work based on work that Rick Johnson and others initiated for Canvas weave mapping. Recent work just recently published just days ago shows that similar signal processing techniques used for the Canvas weave map can be applied to these patterns, these laid line, chain line, well, particularly the laid line patterns. And so what we're seeing here on the right is an image that's derived from the image on the left, this transmitted light image. And basically it's a heat map showing laid line density. And so it's a fingerprint, essentially. It's a thumbprint. You know, all of these molds were handmade. There's not a single mold that is exactly the same as another. And now we have kind of a quantitative fingerprint marking this mold, identifying this mold. So here's Whimsy, at least as it stands today. On the left, we've got a kind of a copy stand setup. That copy stand, there's a camera there and really 4 lighting sources and a computer with a big red button. And that's sort of a key to all of this, is we're trying to automate this and make it repeatable and easy to use. So sort of a 1-button capture. Put the print in on a transmitted light on a light sheet, and press the button. And so when you press the button, we have a raking light capture. We have sort of normal light capture the image, transmitted light capture. Of course, all in register, all the same scale. Nothing's being moved. No camera being pulled back. No zooming in, zooming out. So these image sets would be entirely repeatable and comparable, one image to another. And then some processing that we hope, is going to be conducted in the cloud. So here's a transmitted light image of our sheet. We render that into these heat maps of wire density, effectively. And then we can compare them. We just build up a library and do sort of query and retrieval stuff and identify where this mold has cropped up before. That's the idea. And so this is where we are. This is the prototype, and this is on my brother's kitchen table. This has been a pandemic project. We work on this from time to time. He's an electrical engineer. We have this light sheet below, this electroluminescent light sheet. It's about 1 millimeter thick, so hopefully it can slide under like matted prints, for example. These are the armatures have these LEDs embedded in them. So those are our lights that you're looking at. About a 61 megapixel camera. This controller box on the right. The dog is an accessory, doesn't come with the kit, but we can talk. So the idea for this is really high throughput. To get to scale fast. For this to work, we need not just 10 or a dozen high quality images. What we're hoping to get is hundreds and hundreds, potentially thousands. So we want to make it portable. We want to make it a box, essentially a case that shows up with you get on YouTube, you assemble it, and you can be up and running quick, just hitting that red button, and all your light positions and all your image acquisition is automated. And in that kind of context, if we go back to sort of this watermark, there are these certain nodes where the watermark is intersecting these chain lines. And so watermarks in this context kind of become a bonus, where we can, kind of make essentially another thumbprint, this pattern, now stands for that watermark. And if we can, we can find that pattern where the watermark design, these nodes where the watermark design intersect the underlying mesh, then we've got a really good way to identify watermarks. Of course, things are not so easy in real life as they are in the lab. And what we're thinking of doing, probably starting in the fall or in the winter, is looking at a set of prints. And we're hoping to start maybe with Rembrandt. Rembrandt, there's a lot of work that's been done on Rembrandt recently and actually over many decades. So they're highly characterized, they're highly valued in many collections, but they also exist in many collections, and a lot of collections that maybe don't have access to sort of high-end imaging. They could receive this case and get up to speed and start building, participating in this kind of crowdsourcing attempt to build a library of Rembrandt's papers. Rembrandt is a good place to start. He made a lot of prints, about 300 or so. Here's most of the known prints. But we are anticipating problems. We are anticipating challenges ahead. One, of course, is we're not, Rembrandt, the nerve, he put ink on his papers, right? That he put an image on his papers, and that ink is going to partially obscure, and in some instances completely obscure, the Leiden chain line patterns that we can detect with transmitted light. So we're going to have we're anticipating a lot of kind of flawed or damaged kind of heat maps of our wire densities, right? And that's obviously going to affect our library. But the hope is that if we get to scale, we can start seeing some patterns repeat. And this is one of these things where we're going to have to build a data set to really understand if the theory here is actually going to work. And so, if you're interested in participating, please let me know. And we hopefully, like I said, we'll have a beta test running by the end of the year. And if you want to know more about this, I would point you to the International Journal for Digital Art History, the current issue, online now. And there's a paper on the moldmate identification. And Damon, the previous speaker, also has incidentally has a paper in the same issue. So I just want to thank the co-authors on this paper, Peggy, Sarah, Rick, and Bill. The John Pritzker Family Fund, Amy Rubino is the director there, and my dear friends and colleagues at Yale. Thank you.
Hello, good morning. Thank you, Louisa. Thank you, the rest of the organizers. And thanks to David, Samantha, and Sarah, and anyone else behind the scenes. I know a lot goes into producing a webinar like this. We thought a brief intro to the photo archive would benefit the project that XY and Vardan will describe. And so with that, the Frick Art Reference Library was founded in 1920 by Helen Clay Frick, the daughter of Henry Clay Frick, and after a trip to Europe where she visited Sir Robert Witt, the art historian and co-founder of the Courtauld Institute of Art in London, and its photo archive of 500,000 objects. When toured the archive, she recognized its value and decided to found a similar research institution in New York City. Books and articles at this time were not often illustrated because of the cost, so having a collection of photographs was immensely helpful to scholars at this time. The photo archive was originally housed in the bowling alley located in the basement of the Frick Mansion, and from these humble beginnings, the photo archive now has over 1.2 million reproductions of works of art, of which almost 400,000 have been digitized and are available at digitalcollectionsfrick.org. To organize the collection, we developed an in-house classification system based on national skill of the artist and subject matter of the work of art.
So in this instance, in the upper right, you can see the 221-1 is the classification system. The first two refers to, is for the British School, the National School of the Arts. 21 is for male portraits. 21-1 is a subset for male portraits that are full length. And if we were to keep going on, 21-2 is for equestrian portraits. 21-3 are for three-quarter portraits, and so on. And it becomes as specific as portraits of men with hands, without hats, without hands, with hats, and every combination in between. And we have over 500 of these classification headings in total. This is handy as a benefit of our digital collection site. There's a facet for one to search based on these classification headings. So if you know what a work of art looks like, you can see, you can find it based on the classification heading, not necessarily through the artist. As we move forward, the non-digitized remainder of the photo archive has not had classifications assigned to the photographs. And assigning one of the 500 local classification headings to these loose photographs is often the slowest point in the cataloging process. With the tool outlined by Varden and XY, we on the library level look forward to using AI to assign classification headings and allow photo archivists to spend time and energy on other projects and other activities. And with that, I will stop my share and hand it off to Varden.
Okay, thank you, John. So the aspect we chose to focus on in our work was the annotation of digitized images in the Frick Photo Archive with their corresponding labels, as shown here. As a demonstration of the challenge of this task, we have here on the left an actual image of a lady from the photo archive, and on the right, a non-exhaustive list of labels from the photo archive that might apply to this image. Now, for a human annotator, thinking about whether each of these labels applies would take quite some time, especially when this must be done on every one of millions of images in the photo archive. Please take a second to think about which labels might apply. So in the end, this would be the correct labels according to the Frick labeling system. When we first met with the Frick, our first thought was that the new trend in machine learning was to use artificial intelligence for amplification of human effort. Here we can see some examples in medicine and industry of such human effort amplification. And in science, there are even more examples. Here we can see examples coming from biology and from physics. Thus, we decided to use similar augmentation of human effort for digital art cataloging. What we did specifically was to train a deep network on around 40,000 images from the Frick Photo Archive that have already been manually labeled by the museum staff. Now, for the more technical members of the audience, our solution modified the ResNet 152 architecture, which was pre-trained on the ImageNet dataset with a custom designed last layer classifier that was able to incorporate the syntax of the Frick classification system. Take it away, XY.
So around this network, we designed an app using the Zooniverse website, which many of you may be familiar with for validating the predictions of the AI. And we called this app Henry Clay Tinder for this interface where the network prediction is annotated on the top of the image. And if the user agrees with the prediction, they swipe right. If not, they swipe left, hence the name. And this Zooniverse interface is very flexible. Here you see that it has a desktop environment as well. And this solution is built on a pipeline of pretty well-tested machine learning and image processing stacks, such as PyTorch for training the network, ImageKit to generate the annotated labels, and also Zooniverse, of course, to create the app. And between August of 2019 to 2020, 15, I think, volunteers from the Frick used this app to just test the validity of the AI predictions on what ended up being over 8,000 different images. Shown here on the images, the output we see from the app. You see here we have the image name, the network's prediction, what the human annotator responded, the username of the annotator, and also whether that person is a Frick staff member or just a summer intern. And generally, we achieved pretty good results in the sense that the human annotator agreed completely with the network. So all of these constituent labels are correct 67% of the time. And even on the incorrect labels, we see some examples here. You might even see some familiar names in the usernames. The mistakes are usually just one component off. For example, with hands, without hands, with hat, without hat. So it's very close to doing well. And so the point of this project is to convey this idea that machine learning has been amplifying human effort in science, medicine, and industry, and this data that's available through digital photo archives is very well fit for this same paradigm of, in this case, curatorial amplification, where we generate the metadata, and to ensure quality, there's a human annotator. And there's this synergy that we hope to demonstrate with this project that can be found between digital art history and the advancement of AI research. Hopefully we've conveyed that in the time we have, and thank you for listening, and I guess I'll be happy to answer any questions in the chat.
My name is Lucas Click. I'm the head of digital humanities research at ITATI, the Harvard University Center for Italian Renaissance Studies in Florence, Italy. And rather than running the risk of our website crashing during my presentation, I've pre-recorded it, and so I will play it now. PHAROS, the International Consortium of Photo Archives, is a collaboration between 14 European and North American art historical research institutes working to create an open and freely accessible digital research platform to provide consolidated access to their collections of photographs and associated scholarly documentation. We collectively own an estimated 25 million photographs, forming the largest collaborative and collection of images for the field of art history. We have a grant from the Andrew W. Mellon Foundation to work on the first phase of this project that uses the ResearchSpace platform, a semantic web research environment being developed by the British Museum. So today I'll share with you some of the work that we're doing that leverages computer vision to be able to match artworks across collections, as well as find artworks that are visually similar. Many of the collections have photographs that represent the same work of art. So the aim for now is to be able to merge and aggregate data from various providers into a single artwork record. We also want to be able to provide unique identifiers for these artworks. While many existing vocabularies, such as the Getty Union List of Artist Names, provide data about artists, we don't have any knowledge bases on the web that can provide these identifiers for artworks so that scholars can reference them in scholarly publications and across the web. So I'll do a quick demo of the visual search functionality of the platform so you can get a sense of how we're using computer vision to create these connections between artworks. We provide a user interface for public users that allows them to upload their own images to find artworks that are visually similar in the same way that Google Image Search does. So if a user has a URL for an image, they can paste it here and find corresponding records in the Pharos collections. Clicking on one of the results, they can then visualize that record with all of its associated metadata. We also allow staff from partner institutions to log in and match up artworks in their collections to those of other institutions. We have two user interfaces to support this functionality. In this more simplified view, you can see the image and a limited subset of metadata. Staff can quickly compare two images and click the same button to merge these two records into one. As we can see from some of the results, we're able to find image pairs even where the images are significantly different from one another. We can find images where the frame has been removed, when we have different croppings, when one image is in grayscale and another is in color, when we have variations in the angle in which the photograph was taken, and even when one image is a copy of another. Clicking on one of the image pairs, we're taken to a more detailed record that allows us to compare more of the metadata from these institutions. Clicking on the image, we're able to view both photographs in a IIIF viewer that allows us to zoom in and perform a more in-depth comparison. Currently, we're using two visual search APIs. One is called Pastek and another is called Match, and both provide a different set of results. Here we can see the visual similarity score that Pastek is providing, but as we add more computer vision APIs, we'll be able to see the scores from additional tools together with the textual similarity score for the title of the artworks. We'll also support different types of visual similarity when the images are perhaps not the same, but have some relationship that we would like to make a statement about. And this statement would be in the form of an assertion which would be attributed to that individual. Once the artworks are merged, you can see how the record becomes much richer as we have data from different providers that is aggregated into one record. These data are often complementary, as different institutions focus on different aspects when cataloging the record. The source icon here indicates the provenance for each piece of data. If this artwork is similar to other artworks, we also have another tab that allows users to discover these related works directly from the work record. The idea is that as institutions begin to match up these artworks through a manual process, we'll then be able to take this similarity data to build and refine new machine learning models that will then be able to make the artwork matching process fully automated. Using similarity data, we can also train the model to find images that are not the same artwork but have other types of visual similarity. Finally, using IIIF, we can also allow users to select portions of an image and perform a real-time search across all the Pharos collections of that detail in other artworks. In addition to visual search, we'll offer a wide range of advanced search functionality that allow researchers to combine data from various knowledge bases like the Getty vocabularies, GeoNames, Wikidata, VIAF, and WorldCat. The Pharos platform is currently in development, but we hope to be able to publish the collections and the visual search interface in January of 2022. Thank you.
Oh, hello, everyone. I'm Sofia Oliveira, and I'm a research engineer in the last years, I've been working with OCR and HDR in the context of cultural heritage. So I'm going to give you a quick tour of OCR and HDR technologies. So first thing, what are OCR and HDR? So OCR is the conversion of images of typed, handwritten, or printed text into machine-encoded text. So most of the time, HDR is considered as a subcategory of OCR. One of the main differences is that OCR and HDR is at the OCR is at the moment in an advanced state, but we can qualify as advanced, whereas HDR is in a more early phase. So OCR has been around for quite some time. In fact, the first patents for OCR engines date back to the 30s, but it has evolved a lot, especially these last years. And in these last years, they have facilitated the access to scanned documents and collections through textual search. So I want to give you a general understanding of how modern OCR engines work. So an OCR engine is usually composed of two major components, the text detector and the text transcriptor. So in the text detection module, the goal is to find text blocks or words in the image, and it's mainly built on object detection systems, the one that we use for finding cats, dogs, etc. Then the text recognition module is responsible for transforming the input image into an actual machine-readable text. So in the first step, the image is transformed into a series of descriptors, similar to a series of columns numbers. And this type of network is called convolutional neural network. Then in the second block, the recurrent neural network is responsible for capturing dependencies and relations in the sequence and transforming it into character score for each descriptor, which is represented here as a 2D matrix. And then in the last step, the character with the highest score for each column is computed and assembled to predict the correct text in the image. So this system is called convolutional recurrent neural network, and most systems today are based on this architecture or are variations of it. And as you probably have already heard, neural networks need to be trained. And in order to be trained, they are shown a lot of pair of images with, on one side, images with text and their corresponding transcriptions, so that the system is able to learn how to transform the text in the image into machine-encoded text. So what is the current status of OCR? Well, in terms of performances, it really depends. It depends on the type of data you are working with and also on the amount of annotated data you have. Usually, it's more difficult to find good engines for handwritten text than for printed text, because the data is, there are less data for handwritten text. And with engines that have not seen samples from your collection or from your type of documents, the performances vary a lot, and it's difficult to give general numbers. It can go from low accuracy, for example, in the case of Thai text in degraded manuscripts, to very high accuracy in the case of nicely scanned modern printed books in English, for example. But as soon as you specialize the engine, which means that you train it on samples of your own data, then the performances greatly improve, and you can expect as little as a few % of errors. So really recently, the HDR engines have made huge improvements. Then regarding the remaining challenge, well, there are a few, but I'll talk mainly about two. First, the data. So neural networks need annotated data to be trained, and high quality annotations are expensive in time and resources. Experts needed to annotate it because, particularly in the case of handwritten text, not everyone is capable of reading all the handwritings. And also there are languages and alphabets for which the annotated resources are low, which is very often the main limitation to have good OCR engines for these languages and alphabets. Another challenge in HDR in particular is the different hands and high variability in writing styles that make necessary to have specialized engines, and so the need for annotated data. But fortunately, in the last years, there have been recent works that have been gave very promising results with neural networks that are able to generate very realistic synthetic handwritten data. So just to give you an idea of what are the possibilities of these networks, In the image here, there are only 5 words that have been written by real hands. The other ones have been generated by the network. So you can see that they are quite convincing. So with these progresses, we will certainly have better specialized models at lower costs, since you don't need to have people annotating it and you can directly generate the data. Then another challenge is regarding the accessibility of OCR engines, because most commercial solutions mainly deal with printed text with low performances, usually for handwritten text. There exist open engines that can be used to transcribe handwritten text, but most often they require programming skills and a lot of data to be trained. So we lack ready-to-use services or platforms for handwritten text. So in particular, in academia and cultural heritage institutions, we would need to have more open and collaborative platforms in order to be able to share HDR engines, models, data, so that we can, so that this could improve the general performance of these engines, but also allow people to have access to state-of-the-art technology in HDR. So this is, for example, what the READ Co-op team is trying to do with their Transcribers platform. And I think this type of initiative is a great opportunity to push the community in this direction and improve the state of HDR and give it access to most people. So I will conclude with this and hand the mic to the other participants. Thank you.
Great. Thank you so much. Thank you, everyone. Could we get all the panelists to turn on their cameras and microphones for the Q&A? And I've seen that the panelists have been very busy in the Q&A box answering all but 2 of the questions that came in. So if you did post a question, the answer might already be there. So I saw a lot of questions come in for Damien, and there might be one that's still open. Samantha, is there still?
No, I mean, there's one that's being answered now by XY and kind of a long one that came in for everybody.
So maybe I'll ask XY, you've been kind enough to be typing into the answers. Any of the questions stick out to you that you could share or expand on?
I guess I can directly address the one that I'm currently typing an answer to, which Tamar asked, what if we have this, I guess, double wrong scenario for the app that we developed, where, for example, the app is incorrect and the content of the images might be rather difficult for the annotator even to make a decision on. There's 2 aspects to this problem. I guess maybe John can chime in as well, because we have had this conversation before, which is there. So for most of the images, this is not a problem because the Frick staff have been expertly trained exactly to recognize these images. There are some problematic categories that John, I guess, could speak about. Right, so that's the first aspect. And the second aspect is deep neural networks are, there's this analogy that's deep neural networks are like a pet. You can train them to do things you know can be done, right? And they like, we talk about superhuman performance, but it's more of a buzzword. And like, let's not get into that. So if a human can't even do it, then it's unlikely a network can do it. A network can be faster, it could be more precise, but if the information just isn't there or isn't conclusive, you can't train it to do that. So those are the 2 aspects, and I guess John might chime in about the vague labels.
Yes, there are certainly vague labels. 2 experts with 20 years working at the Frick classifying things. One could say this is a genre bucolic scene. and the other might classify it as landscapes with buildings with cows. And those are two different classification headings, but they actually both apply. And there's a lot of nuance there. You'll see like the British ones will tend into the landscapes, where the Dutch ones will tend into genre. And the computer has done pretty well picking that out. Stylistically, where those go back and forth. But yeah, there are, most of these are pretty clear. The portraits, the Bible scenes, like we've had really good experience, like even the difference between like a deposition versus a resurrection, where just whether or not the person's horizontal or vertical, it's not that the scene isn't that different. But yeah, it is based on what goes into it. So we have 100 years of people classifying certain things as genre, certain things as landscape. But then if someone now disagrees with it, there is that nuance, and it's not to say what one is wrong or right, but it is an issue with the system where certain things where there's a gray area between the classification.
Great, thank you. I've got to take a question from my former colleague, Jim Coddington, that Paul Messier was answering, but maybe you can expand, Paul. Might you find a base mesh with different watermarks? Would this simplify or complicate the history of paper making and the sources of papers for artists?
You could definitely, sure. I can imagine a scenario where, a watermark, the wire applied design needs to be repaired, or it gets out of register, or maybe the mill changes hands, or something, changes their branding strategy, but they keep the mold, and they put a new watermark in there. Yeah, I mean, in theory, if this method proves out, we should be able to see that. We would be able to see that that base mesh is consistent, but the applied design is different. Now, what that does to the history of paper making, I'm not sure. I think it probably is a complication, but this kind of research is all about complication and not taking sort of received wisdom at face value. And if it's a reflection of reality, of nature, then we've got to incorporate it.
Great, thanks, Paul. And we had a number of questions come in for Damien, and one I was particularly interested in. Do changes in camera sensors and technology pose a possible problem for measuring change across pairs of digital proxies?
Sure. Yeah, I mean, I think for the method I discussed today, just sort of these color measurements, I think the lighting is probably the thing I'd be most worried about. But yeah, I mean, there are like optical effects and stuff like that. Usually though, with very like carefully controlled observations or calibrations, you can kind of remove those effects. So that'd be the hope. But, in such a short talk, I don't think I was able to give like full attention to all those problems. I mean, it's not, I don't want to make it seem like those issues are trivial, because if you're trying to make highly precise measurements across different sort of setups, then yeah, that's a very technical problem. But certainly, we certainly corrected for different lighting conditions, and now we're folding in like collections from other places that were photographed in completely different way. The YCBA collection I discussed was scanned under exactly the same protocol. It was all done at once and, to the same spec. But now that we're like bringing in these other collections, we're confronting this issue. So even if, color correction was done on all of them, well, was it done in the same way? And so, this is certainly a technical issue, but the hope is that, there are ways of controlling for that. Yeah.
Great. Thank you. So thank you all once again. If you have questions, please keep those posted in the Q&A, and the presenters have been very prolific about getting to those. I also want to thank the first half of the panel session for packing so much information into 7 to 8 minutes. That's an amazing feat. So thank you very much for doing that. We're going to take a very short break. We'll be back in about 4 minutes to start off the second half of the presentations at 12:10. So go get yourself a cup of coffee and we'll see you back shortly. Thank you.